Hello and welcome to this lecture where you are going to learn the basic intuition about 4 more tracking algorithms. The first is MedianFlow, which is not suitable for fast-moving objects or objects that change their appearance quickly. For example, if in one frame the object is far from the camera and in the next frame the object is too close to the camera. The main concept of the algorithm is that it tracks the object in forwards and backwards directions and measures the differences between these two trajectories. For example, in this image, we have the previous frame and the posterior frame. To know the next location the object will be, the algorithm calculates the difference between them, so we know if the object is following the trajectory correctly. The algorithm is not suitable for objects that change appearance, according to this definition here, because of this calculation of similarity between frames. If here, where I am pointing the mouse, the runner changes its trajectory upwards towards the grass, the differences between the trajectories will be too large and it will not be possible to continue tracking. Based on this calculation, it is possible to predict tracking failures or when the object leaves its position. In this example, you can identify if a runner is going out of his or her lane and is invading someone else's lane. This image shows how the algorithm works. We have the previous frame, t-1, the current frame, letter T here, and the arrows indicate the direction of the next movement. This other image shows the calculation of the median, which is a statistical concept, to calculate the differences between frames. If the difference of the median is small, the object is heading in the same direction. On the other hand, if the difference of the median is big, the object has changed direction. This is why this algorithm is called MedianFlow, because we are calculating the direction of median values. The next algorithm is TLD, Tracking Learning Detection. This diagram shows the structure of the algorithm, which is composed of 3 parts: tracking, learning, and detection according to its name. The first step is to start tracking the object, and while the object is being tracked, the data is sent to the learning process, so it adapts to tracking. While the algorithm is learning, it is online learning, the object detection process is improved, and the detection data is sent back to the learning process. When tracking fails, the algorithm tries to learn from its errors and sends the data to try to detect the object again. We are not going to see mathematical details, as the goal of the course is just to show a general overview of the algorithms. The next algorithm is MOSSE, Minimum Output Sum of Squared Error, which is one of the fastest but not so accurate. It's a good option if you need tracking speed and don't care so much about quality. The algorithm is robust to lighting variations. For example, if the light is on in the first frames and the light is off in the others. It's robust to scale. If the object is near or far from the camera, It is also robust to pose. For example, in the first frame, the person is facing the camera, and in the next frames, the person has his or her back to the camera, or when the person puts the hand in front of the face. In order to identify these changes in the environment, the algorithm uses a mathematical concept called correlation filters. This image shows how the algorithm works. In the first frame of the video, you select the face or the object you want to track. It is the initialization phase. See that the image is quite dark. And in the next frame, when we increase the light, the algorithm continues tracking the person's face. Frame 150 and frame 250. This red point indicates the center of the detection. And here we can see more information. We have the inputs, which is the object, the application of the correlation filter, and the output with the result of the object that was tracked. We can see only this center point here and here. Finally, the last algorithm is Goturn, which means generic object tracking using regression networks, which was trained using offline learning. This is the only algorithm with this feature we have seen so far. So it was trained using datasets composed of thousands of videos. It is based on deep learning and convolutional neural networks, which is a type of neural network widely used for image classification. Here we can see the architecture of the algorithm, which starts by the definition of the object you want to track. As we can see here, this image is sent to 5 convolution layers and 3 fully connected layers, so that we get a prediction of the object's location. The neural network returns a bounding box, as you can see here, with the position of where the object is in the next frame. Don't worry about understanding neural networks, because as I mentioned before, the goal of the course is just to show you the basics of each algorithm, and you can access the additional materials if you want to know more. Goturn doesn't have very good results because we need to track objects like the ones the algorithm was trained. For example, it will not be able to track fingers because it has trained with hand images. So, before using it, you need to check the objects that the algorithm has been trained on. Of course, you need to perform some tests to see if the algorithm will perform good in your application. Finally, we have a summary of some of the algorithms. CSRT has the best performance, but is the slowest. KCF is not very good regarding quality, however, it is a very fast algorithm. On the other hand, MOSSE is the fastest of all. It is important to know these features of the algorithms for you to choose the best one according to the type of application you are developing. There are some applications where you need a lot of precision and speed is not so that important, so you can use CSRT. There are also some applications where the quality is not as important as speed, so you can use KCF or MOSSE. In the next lecture, we are going to start the implementations. See you there!